So Cairo, the paper Cairo here on my left, has this memory, write once memory thing, which is this primitive where you can kind of like read write memory, but you can only write once and then you can read as many times as you want, which is kind of a natural thing to do in circuits when you're using constraints, where basically a memory access is, as you can see here on the left, a tuple AV, where A is the address in memory and V is the value you're reading or writing. So basically, what the constraint will be is that it will enforce that this is true in memory. And so the first time you read, it's sort of like you're writing, and as long as all of the accesses to the same tuple are the same, whenever A is some value, V is always the same value, which they call single valued, is correct, then we have this write once memory. So I'm going to explain how that works. And basically, first let me introduce what their memory does. They have this M thing, which basically says that it starts with the program, and then there's some public input and then some public outputs, and all of these things are public. I believe that's the layout, but I'm not exactly sure, but probably it's something like that. And then if anything in between is like the memory that the program can use during runtime. So it can write to this memory. It can and actually the public output is also memory that it's writing to and that you're retrieving at the end. But you can think of it as the memory that you can use to write and then read as many times as it wants once it wrote somewhere. And of course, this memory is indexed, so you can think of this as 1, 2, 3, 4, 5, and so on. And these are the addresses of the memory. And so what's gonna happen is that we're actually not gonna use something like that. We're gonna have a column instead, or two columns instead, called A and V, which forms the L1 list here, which they call, and this column is gonna represent, as we go down our program, is gonna represent the memory accesses that we're doing, and we're gonna prove that it's equivalent to memory accesses to the memory that has such public input and program and public output. And we're going to prove that the memory is consistent with whatever Cairo is expecting. So we'll see what that means. And I just want to mention also that basically this whole thing happens during proving if you understand all these arithmetization like air and Planck and whatever, you know that the prover has like different registers, let's call them R0, R1, and different values as they go down the circuit, as they step through the circuit. And these get committed as polynomials and sent to the verifier. And so if you understand that, you can see these new columns as also columns that will be sent as commitments to the verifier. But you will see that we're also going to add another L2 column that needs to be constructed after these first columns have been sent to the verifier. So these things are going to be sent to the verifier, and then we're going to construct. We're going to get some challenges, specifically point Z and some randomness alpha. The two of them are random, and then we're going to construct these columns and send that to the verifier. So we're sort of constructing an execution trace in different steps in this protocol. Okay, so L2 is A prime, V prime. And basically, if L1 is memory accesses that are, for example, here I'm reading memory A at address, memory at address 1, and it's the value 3. Here I'm reading, let's say these are writes, write at address 1, it's the value 3. Write at address 5, the value 4. Then we can read from address 5, the value 4. these are unordered, you know, then L2 is going to be exactly the same list, but ordered. So it's going to be 1, 3, 2, 3, 4. I don't know what the values are here. Then 5 is going to be 4. We know that. And then we're going to have 5 again, 4. And already you're noticing that sometimes the values repeat. But the values repeating is okay because we'll see here on the left we're checking for single valued. You'll see what I mean. But before I get into the constraints that are going to verify that these things are okay, I just want to point out that this is it. This is sort of the or at least half of the scheme, which is that here on the left we're getting we're writing the accesses in memory that each row or each step of the VM is doing. You know, this corresponds to the different rows of the execution trace. And here on L2, we're writing the same list of accesses and values that we're reading or writing from these addresses, but ordered. Okay, it's 1, 2, 3, 4, 5, 5, etc. And that's gonna be enough, as long as that list makes sense, and as long as also something I should mention, as long as the beginning of the list is the program and the public input, and the end of the list is the public output, and you'll see that basically we'll verify these things. Well, I'll talk about that later. Okay, so let's look at the constraints that we're building. These constraints here are both gonna verify that the memory is correct according to Cairo, and that L1 and L2 make sense according to each other. So let's look at continuity. Continuity says that either AI plus 1 prime is equal to AI prime. So this is what we're seeing here, for example. Two rows following each other are the same. Or that AI plus 1 is equal to AI plus 1. So this is this thing, or this thing, or this thing, or this thing, right? We're seeing an increment of 1, not of 2, not of 3, of 1 or 0. This is what we're seeing, right? Doesn't change. Increment by 1. All right, this is what we're seeing. And the reason is that we and this is I believe why we want to order why we're doing this ordered list of accesses, because we want to make sure that accesses are we're accessing all of the memory. And the other reason why we're sorting things is also going to be for the single value property, which is going to be easier to check. The single value property is the second thing here. What does it say? It says that either vi plus 1 equals vi. So either we have this thing here, or we have that the value, so the value is the same, or if the value is not the same, we know for sure that we've seen an increment by 1. So if these two values here were not the same, for sure we would have seen a 6 here, basically. So if they're not the same, but the accesses, the addresses being accessed are the same, then we have an issue, right? Because we're reading two different values, and that's not working. So this is why we have this sorted list, because it would have been really hard to do it without a sorted list. And the sorted list cannot be built from scratch, because when we run our circuit here, we don't know, we're gonna access memory in different positions, and it's not gonna be ordered. So finally, we have to prove, what do we have to prove? Hopefully you're convinced that this is enough, except that we haven't proven that this list is equal to this list. And proving that two lists are the same is basically called a multi-set check, or like a permutation argument, because you're proving that these two things are permutations of one another up to some permutation that we don't really care about. Okay, so how does this permutation thing works? It's the same as Plonk. If you understand Plonk, it's going to be easy. But the intuition is that, okay, let me write the intuition and then I'll explain the constraints here. The intuition is that you have a list, AIVI, okay, you have a list of tuples, and you want to check if it's equal to another list of tuple. And comparing tuples is not really something we can do, except if we receive some randomness from the prover, and I said we have some randomness alpha. Then we can encode these tuples as AI plus alpha VI as a random linear combination, and this should work, of course, some probability. And now we're comparing actual values instead of tuple. Okay, so we've sort of reduced the prime to comparing values instead of comparing tuples, or list of values instead of comparing a list of tuples. The next reduction is going to be to try and compare two polynomials. I'm going to want to compare this polynomial, x minus AI plus alpha VI, and this one, x minus, maybe I'll write like this, maybe that's clearer. Oh, missed the prime here. So what I'm doing here is that I'm trying to compare two polynomials that have the same roots. And the roots are the items in my list initially. So that's the second reduction. I'm going to do a third reduction, and I'm going to say this is basically the same as proving that, okay, I'm going to write like this. If this thing is A and this thing is B, is the same as proving that A over B equals 1. Okay? And, okay, maybe I'm going to write the whole thing. It's going to be nicer. Okay, duplicate this. Up. No. Proving this thing is equal to 1. Okay? And I'm going to do another reduction. We're going to use the Schwartz-Ziegler lemma to say that if I get a random point z, which we also receive from the verifier, and I just check that this is true at z, then it's enough, and we're convinced. And so basically, what's happening on the left here, the permutation thing, is that we're going to build this grand product here on the left, bit by bit, because remember we can only access I'm looking at the values here. We can only access the first row or the first two rows, because in air we're doing things with pairs of rows, and then the second pairs of row, and then the third pair of row, and bit by bit. So since we cannot access values at random in the table, we're gonna build it row by row. And the way we're going to do it is we're going to use a new column called P. And a column is going to be built, the P column is going to be built, let's say here, is going to be built afterwards as well. And actually, actually I made a mistake. The Z and alpha we receive here, Z and alpha, after we've committed to all these things. So we're constructing a column after we've sent the other columns to the verifier. Anyway, so how do we construct P? We say that the first value is going to be 1, and the last value is going to be 1, because this is what we want to check here. And we're probably going to use boundary constraints to enforce that. And then we're gonna say, this is what we want to say. We want to say that Pi equals Pi minus 1 times times I'm going to write it like this, z ai plus alpha vi divided by z minus ai prime plus alpha vi prime. And if we look at how they did things, we have to construct p 0 equal 1, and which I think they forgot, maybe I misunderstood something, but also the final value p minus 1 is also going to be equal to 1, which they have one here. Final value, and initial value here, which I'm going to ignore that for now, but you can try and understand why mine is different. And then the cumulative product step here, which they wrote a bit differently because we want to avoid division. We're going to move this on the other side here. And it should look like what they wrote. Maybe it looks exactly like what they wrote. So we're good. And of course, when we're going to encode that we're going to try to prove that as polynomials. We'll be writing something like a constraint like that, p g times x to do the switch to the next row, times z minus ax plus alpha vx, minus px times z minus these are all going to be polynomial these are going to be polynomials, so we're going to write a constraint that looks like this eventually. Okay, so again, we proved that our list L1 and L2 have our correct accesses, that when they where the second list is sorted, and also the accesses make sense in the sense that once you see that an address in memory has a value, then you'll always see the same value. And then we proved that the two lists are the same. And I guess that's the first part. Hopefully that makes sense. And the second part comes here. They say, okay, but we really need to prove that the beginning of our stuff contains the program and the public input and things like that. And so their technique here is to do a bunch of dummy access to 0, 0 here. So they changed the first, change that. They changed the first, let's say we have a program of size 3, okay? That's our public input or program. So we just do a bunch of access to a bunch of zeros. Then what's gonna happen in our product is that the first multiplication here, by the way, I haven't changed anything here, right? In our product, the first items here are going to be z minus 0 plus alpha 0. And we're going to have that L times, right? Remember? Because of this here. And so basically, because we did that, we're going to have a thing at the very end, a product at the very end that's not equal to 1 here, but that is equal to, well, imagine that if we had added the, all right, never mind. That something that will be equal to, on the nominator to, because it was not cancelled by the bottom, will be equal to z times z times z L times. And here in the paper, they call that z to the power the size of that domain A. And that domain A is basically the domain that allows us to encode this public input here. So this m star is defined somewhere else in the paper, but it's the thing that it's the function that given an index or a domain will give us the values, and this domain is the domain to represent the program or the public input. Okay, and so that's not all, because we have a bunch of z, but we also, on the other side, on the L2, we actually use the correct, presumably, right? We use the correct values to read from the correct program values. So imagine that 1, 2, 3, all of these things, actually 1, 2, 3, because we say it's size of 3. The value here contains the actual program. So it's like m star of 0, m star of 1, if we're using the index 0, 1, 2. And so in this grand product, here we're going to have something that's not, here in the bottom, we're going to get something that's not canceled here, and it's going to be the actual values of our program. And so we need to cancel it, and it's going to be canceled here. Or basically it's going to, again, instead of 1, it's going to appear, here. Oh, so that's right. Sorry, this is really drafty. We have ZL here, and here it's going to appear Z minus 1 plus alpha m star of 1 times, and it continues and that represents the program. And that's going to be the final value instead of that final value 1. And so as the verifier, we just have to make sure that the boundary constraint here doesn't check that it's equal to 1, but it's equal to this thing here, which we can compute as the z times L divided by the multiplication of this multiplication, where we have the program and the public input being encoded here. So hopefully that makes sense. Maybe it's a bit confusing, but maybe you can read that part of the paper and watch my explanation, and hopefully that makes sense. This technique is also used to do permutation, to do range checks, but I'm not going to explain that here. And you can sort of see the actual, in this section after list of constraints, you can see the actual constraints that they use. And so you can see the continuity thing here, the value singleness, or I can't remember how they call that, the single value thing here, the grand ratio, I guess, and the fact that the last value of the grand ratio should be equal to the memory of the program, the program. And why do we have another one here? Oh no, this is just the initial value, which I haven't explained, and this is the normal one for the product. Okay, I'm gonna stop here. Kind of a messy video, but hopefully it helps someone that's trying to understand this part of the paper.